Hello everyone. Today we are going to start our first session or lecture on Introduction to Topology. Some things I wanted to say. I will not be following any particular textbook, so I am not going to mention any useful text or anything here right now. But as far as I will continue my lectures, I will be quoting the textbooks or the research papers which one must read in order to explore the subject more. So let me start with the content. So what I planned for today is to give a motivation to topology which you might not have seen in the classical textbooks like Muncrace or Spanier, Simmons. They have written the ideas whatever I'm going to talk today, but in a very different manner. So let's not talk about it more. Let's directly begin with the topic. So topology. So let us first understand this word topology. Since it's a most of the terminologies in mathematics have some meaning. So this word can be interpreted as this. So this is my interpretation. So there can be various other interpretation. I am not saying that this is the only one or this is only right, but yeah, it's a logical way to understand this word. So if I break this word somehow like this, topos plus logic. So it is topology. Logic, you might know what is logic. Like, I am not talking that you should produce me a definition, a formal definition of logic, but I think you are aware of this word logic. Topos, as far as this word is considered, this is a Greek word. What it means is, it means place, to be precise. So what I'm gonna write, topology is a branch of mathematics which provides a platform slash place for logics to develop the further mathematics. So that is totally mine. So I can write my name also here. Okay, so let us continue. So topology gives you plenty of logics, plenty of things which you can apply in various other mathematical subjects. Not only mathematical, in fact physics. In modern days this subject is being applied to finance, this subject being applied to artificial intelligence, which nobody has thought. I think Hausdorff hasn't thought, or the Bourbakis haven't thought at that time that this subject will be that much useful at some point of time. So that's why I said it's a platform, it's a place which provides logics for further mathematics or for further mathematics development. So let me now once again, this is just a philosophical interpretation of this word topology, and you will be observing this, that whatever I'm saying, it is true. It is true almost everywhere. Like you might know, on a set of measure 0. So one more thing I wanted to say, as far as prerequisites for topology is concerned, there are many, but like abstract algebra, you should have a knowledge of abstract algebra, basic knowledge. You should have a basic knowledge of real analysis. You should have a basic knowledge of linear algebra. So we will be assuming few of these things, but the concepts which are like bit more complicated, I will be explaining that, and I am assuming that the student has, or the viewers have studied at least 2 years of undergraduate mathematics. Okay, so let me now begin with a motivation for topology. So everything in mathematics begin with a set. So let X be a set. Now, as you might have seen, alone sets have, you can compare two sets. There are many operations like union, intersection. One thing which I am interested in telling you, how you compare two sets, or if you have two sets, okay, say X and Y be two sets, then I think you guys are familiar with this logic. The cardinality of X is same as cardinality of Y if and only if there exists a 1-1 on 2, or some people call it 1-1 correspondence between X and Y. So basically there is a 1-1 on 2 map from X to Y or from Y to X, one and the same thing. So you see, we are comparing two sets, like when two sets are same or equivalent. So how I would like to say, I like to define a relation. Let tilde be a relation on collection of sets. So you can say all sets. Note that this collection is not a set. If you want to know about, okay, let me write it as a remark. Collection of all sets is not a set. So if you want to know about, that's why I have just written collection. I haven't written sets. So if you want to study about this, I will prefer you refer to the book by Modern Analysis by G.F. Simmons. I think in very first chapter he provides a beautiful argument to show that collection of sets is not a set. So okay, let me continue. So what is this relation? X is related to Y if and only if, or if there exists a 1-1 on 2 map. Okay, I should have it written map here. Map between X and Y. So like for example, let me present you two examples. Okay, I'm not gonna prove it, but I'm just gonna give you a visualization for it. So let us assume your set X to be I cross I. What is I cross I? I means a closed and bounded interval 0, 1. I will be using it many times. So if you want to plot your x, this set I am talking about. Or let us take the boundary of this. Or no, let us have this only. We can have boundary. Let us take the boundary of this set. So boundary of this set. So what I mean by this thing, I will be later on introducing the symbol del. So I mean this thing, all x comma y such that okay, or for the moment let us all x comma y such that it has this form, like if x is 0, like if you are here, then your y should be lying between 0 and 1, or x is 1, then your y is lying between 0 and 1, or y is 0, x is lying between 0 and 1, or y is 1, x is lying between 0 and 1. I know I can write it in a better fashion, but it's fine. So basically, what is my x? So my x is this set. Cross 0 union 1 union singleton 0 cross 0 1 union singleton 1 cross 0 1, closed and bounded interval 0 1. So basically this thing, let me draw it with red color. This thing. Okay, very nice. So this is 1, this is 0, this is 1, this is 1 comma 1. Now guys, let me take another set. Let us take y to be all x comma y in, of course, R2 such that x square plus y square is, say, 1. Okay. Now my claim is x is similar to y. So let us call this example as example 1, because we will be referring later on to this also. Okay. So my claim is x is similar to y. So what is y, guys? So y is this circle. So sorry for my bad drawing. So this circle, 1 minus 1, 1 minus 1. Sorry, plus 1 minus 1. So basically this is a circle with center, origin and radius 1. Very nice. So how we can see that like this is a bijection? So the idea is, you somehow, you see, if you take a smaller circle, say of radius, or let me do like this. So you have this circle, okay? This circle, basically y, will be similar to a smaller circle, right? Say a radius of circle centered at origin and with radius, say, 1/99. Okay. And center is origin. Why this would be similar? See, clearly you have a bijection. Have this smaller circle inside, this is outside. So if you take any point here, and you extend from center to this point, you will have a point on the bigger circle. So you see, this is your 1 1 onto map. Similarly, if you have any point here on the bigger circle, you join from the center, so you will have a corresponding point here on the smaller circle. So you have a 1 1 onto map between these two circles. Now what you can do, so see what is the situation now. This smaller circle is somewhere here, and you have a box, right? This is 1 by 99. Now what you can do, you can shift your origin, or you can translate this smaller circle, or you can shift its origin somewhere inside this box. Which box? Basically this thing. So now you will have, if you shift the origin, you might be aware of this concept from your I think 10th class. So if you shift this origin, this is a simple translation. Basically your map would be, if you have the newer point, say this point is A comma B, okay? So your map should be like this: xy goes to x plus A, y plus B. That is what shifting of origin means, from R2 to R. So your origin will go to now A comma B. So this circle, from here it will move to something like here. Now again the same logic. You take any point on this square. You can join this by this center, right? How many points you are getting on circle? A unique point. Similarly, you take any point on this circle and you extend from center array to via that point. It will cut at a unique point here on this square. So you see, there is a 1 1 onto map between this smaller circle and your rectangle, which was x or square. So you see, pictorially I can prove via maps, but I just want to give a motivation today and an idea today. So you see, in topology you have to visualize a lot of things. So it is better always to have, the intuition, and rather than doing programming, it's better to do with hands or in mind, whatever you can do. Of course you cannot think beyond 3 dimension, and in 3 dimension also it is very difficult. So what we get, x is similar to y. Okay. So what we get is this x set is similar to the set y. So this circle and square are in 1 1 correspondence. Very nice. So let me not begin with another example. I will be giving you many examples, but I think this is sufficient for me to give you the motivation what I am planning. Now, so in mathematics, you might have seen, if you have a set x, you associate various kind of things with this set x. I think you know a few. You can associate a binary operation. So how you write it? Usually you write it like this. You may define the operation to be like, okay, you may define structures like groups. You may take two operations, *1 and *2, and you can talk about the structures like rings. You can talk about the structures like vector spaces if you have a corresponding field F. And what will be the operations? There will be two operations. a plus from x cross x to x, and a multiplication or a scalar multiplication, what you call it, from x cross f to x, and having the properties, the various properties. So you see, we are always interested. What we are interested, what I want to say is, I want to say we are always interested in giving additional structure to the sets, and you know what we talk about then, when those two would be same in the sense, like you might have run in vector spaces, what you have? Isomorphisms, right? Or vector space isomorphisms. Isomorphisms means, morphism means structure, iso means similar. In groups, rings, you have groups / rings isomorphism. And like I said here, when you have alone two sets, we can also define a similarity when these two sets will be similar, when there is a bijection between the two. So when we associate various structures to them, like we make it a set to a vector space, group, ring, we talk about when two objects would be similar. So if you are aware of these structures, can you I can give you a question to think. In example 1, can you make x and y vector spaces or groups or rings or many things you can talk about, such that the spaces, the corresponding spaces, vector space, groups or rings, are isomorphic? You can do this problem if you know little bit about groups, rings or vector spaces. Fine. So what we are doing here is, we are if in mathematics, if we have a set, we assign something to it, some structure to it additional, and we study that structure and we see when two objects will be same. I will be in some lecture later on introducing something called category theory, where I will be generalizing whatever the motivation I am giving to you right now. But I don't want to jump into category theory. I want to have a very classical and basic introduction to topology, such that everyone can understand these lectures. So let me follow a bit abstract approach and finally define what is topology. So definition. After this definition, I'm gonna stop here, and we will be continuing in coming session. We will be seeing some examples of topology of topology or something called topological spaces and so on. So let us first define what is a topology. So similarly, like I said, we have to begin with a set. So let X be a set and tau. I know this doesn't look like tau, but please assume it, the capital or small tau. So it looks like 3. So and let this t or tau contained in 2 to the power x. What is 2 to the power x, guys? The power set of x, collection of all subsets of x, such that now this tau has some properties. What are the properties? Phi comma x belongs to tau. Very nice. Second property, if you have u comma v in tau, okay, if you have two members, then you will have their intersection inside. Third, if you have collection or a family of sets, if u alpha, alpha in lambda, capital lambda, be a family of subsets, not subsets, okay, yeah, fine, subsets of x, basically a family of sets in tau, a members of tau, then union u alpha, alpha in capital lambda will be also in tau. So what it tells you, the third thing, this tau is closed under arbitrary unions. What it tells you in language, tau is closed with respect to arbitrary unions. And what this tells you, tau is closed with respect to the operation finite intersection, because it is 2. By mathematical indication you can say n, finite intersection. Okay, and your empty set and x should be there in tau. That is the third thing we should have. So if tau has all 3 properties, then what we say, then tau is a topology on x, and x along with this tau is called topological space. Fine, guys. So basically, if you have these 3 properties, you are gonna call tau a topology on x, and x tau you will be calling topological space. So like I said, these things. So what is my aim? So if I have, where I have written that, okay, fine. If we are always interested in giving additional structure to sets, and then we are interested in the question when 2 sets would be same with respect to that structure. So similarly, we are giving this very abstract structure tau on x, which has these 3 properties, and we will be calling this tau to be a topology on x, and x tau be a topological space. So let me now finish up with very 2 trivial examples. We will be seeing more and more examples in coming lectures, and we will be also seeing another motivation for this definition in coming sessions or lectures. So let me present you 2 examples. So number 1, this is if you have any set x, you take tau, let me call it I and d. Tau, I suffix I and d, this is phi and x. So you may verify this is a topology. I will be doing more complicated examples. So this is a simple one. You can try it on your own. So tau is a topology on, IND, topology on X and is called indiscrete topology. Let me stop with this example only. I will be presenting more examples later on. So example also X with tau t is called indiscrete space. Also tau ind suffix ind is also known as trivial topology. What? Trivial topology. Now I want to mention one thing. See, there is a distinction between two words, trivial and basic. Basic are very different words. You might be thinking that what is with this topology? This is so obvious. But in maybe next session, I am gonna tell you importance of this very trivial topology. So trivial and basics are two different things. If something is basic, that doesn't mean it's trivial. Like many a times you might have heard your teachers are telling, oh, this is so basic, it's trivial, you should know it. No. So I want to end this lecture by having a quote of my own. Nothing is trivial in mathematics until you know, it will be single L. I am gonna make lot of spelling mistakes, so sorry for that, but not when it comes to mathematics. So the language of mathematics. So until you know how to do it. So nothing is trivial in mathematics until you know how to do it. So remember this, and you guys are most welcome to ask questions in comments, and in the description I will be attaching my CV to know about me. And let us stop with this. So the motivation is like the usual thing. We have a set, we have some structure on it. What is our new structure? Topology. And what we'll be doing, we will be seeing later on how the two topological spaces are same, okay, or isomorphic, but we will be using different terminology here. So thank you very much guys for listening and your patience. Let's meet you in next session. Thank you.